Hello friends, I welcome you on my channel Engineering Mathematics djganit. In this lecture we are going to discuss third standard form of nonlinear partial differential equation of first order. So let us see what is the partial differential equation in this standard form and how to find out its complete integral. So if our partial differential equation can be written in this form, that on one side we have terms containing x and p only, and on the other side terms containing y and q only. That is, we can write our partial differential equation in this form: function of x and p equal to function of y and q. In this equation z is absent, and so if z is absent in the given equation, and if you are able to write your partial differential equation in this form, that is, terms containing p and x on one side and terms containing q and y on another side, then how to solve this partial differential equation? So suppose our partial differential equation is in this form. So since these two are equal, we can assume that suppose both are equal to some quantity denoted by small a. So if both are equal to small a, then we can write function of x p equal to a as well as function of y q equal to a. Now after solving this, we will be able to write p as a function of x, and after solving this we will be able to write q as a function of y. So first we assume that both are equal to a, and then solving these two we find out values of small p and small q as a function of x and y respectively. And after obtaining p and q, we will substitute value of p and q in this equation: dz equal to p dx plus q dy, and then we solve this resulting equation. So it is easy to find out complete integral if our PDE is in third standard form. So we can do some problems. We start with first problem. We have to find out complete integral of these three partial differential equations. So we start with first one. So we write given equation is x times 1 plus y into p equals y times 1 plus x into q. So we try to write down this equation in another form such that on one side we have terms containing p and x only. So I keep p and x here, and I transfer this 1 plus x on left hand side. Similarly, here I keep y and q as it is, and I transfer this 1 plus y on right hand side. So here you can see this is in standard form 3. This left hand side is nothing but function of p and x, and this right hand side is nothing but function of y and q. So this equation is in standard form 3. So what we will do is, we will assume that both are equal to, say, constant a. Then we will have both equal to a. We have px upon 1 plus x equal to a, and also y into q over 1 plus y equals a. So now we find out small p and small q. Small p is a times 1 plus x divided by x. Similarly, small q is a times 1 plus y divided by y. So now we put values of P and Q. Putting values of P and Q in dz equal to P dx plus Q dy, we have P is 1 plus x by x. P equals A times 1 plus x by x. Similarly, Q equals A times 1 plus y by y. And of course, we must write dx. Q is A times 1 plus y over y dy. P is A times 1 plus x by x, Q is A times 1 plus y by y. So this now we can integrate. Before integral we rewrite this as, this is A times, this I can rewrite as 1 by x plus 1 dx. Similarly this I can rewrite as 1 over y plus 1 dy. Okay, now we integrate. So integrating we obtain integral of dz is z equal to A times integral of 1 by x is log x, integral of 1 with respect to x is x. Similarly A times integral of 1 by y is y log y, and integral of 1 with respect to y is y. So A times log y plus y plus arbitrary constant, say log b. So this we can rewrite as A times log x plus A times x, A times log y plus A times y plus b. Therefore, if we combine these two, A can be taken common, ln x plus ln y. Similarly, if we combine these two, we can write A times x plus y plus b. Therefore, z is A times log x into y plus A times x plus y plus b. Okay, so this is required complete integral where A and b are arbitrary constants. Required complete integral where A and b are arbitrary constants. Now next problem is py plus qx plus pq equal to 0. P into y plus q into x plus p times q equal to 0. So let me check it again. P into y plus q into x plus pq equal to 0. So this is also nonlinear partial differential equation of first order. These terms makes it nonlinear, and let us try to write it in standard form 3. So here in these two terms q can be taken outside, so we have q times x plus p equal to 0. So from this we write this as py equals minus q times x plus p equal to 0. So now if we separate we can take this x plus p on this side. P times x plus p equal to minus q by y, and I must not write 0 here. So this is now in standard form 3, p upon x plus p, which is function of x and p, and right hand side minus q by y, which is also function of y and q only. So we assume that suppose both are equal to small a, then I can rewrite this as p over x plus p is small a, q by y, negative of q by y is also small a. So let's try to find out p values of p and q. So from this I obtain ax plus a into p. Here I will have q equal to minus a into y. So value of q is minus a into y. I require value of small p, so I take this term on left hand side. So I have p minus a times p equal to a into x, and this is p times 1 minus a equal to a into x. Therefore p equal to a into x over 1 minus a. Okay, so now we put values of p and q. dz is p times dx plus q times dy. So therefore dz small p is ax by 1 minus a dx, and small q is minus ay dy, and finally integrating we get integral of dz is z. Here a upon 1 minus a constant, integral of x is x square by 2, similarly a as it is y square by 2 plus b. So this is required complete integral. This we can rewrite as a x square 2 times 1 minus a minus a y square by 2 plus b. So this is required complete integral, where a and b are arbitrary constants. So it is easy to find out complete integral if our partial differential equations are in standard form. Now let us take what is third one. Third one is p square minus q square equals x minus y. P square minus q square equal to x minus y. P square minus q square equal to x minus y. So this we can rewrite as p square minus x, and if I take minus q square on right hand side, I will have q square minus y. So this is in standard form 3. On one side we have function of x and p only, on right hand side we have function of q and y only. So from this we can obtain values of p and a. P square is a plus x, similarly q square is a plus y. So therefore p is square plus or minus square root of a plus x. This is also plus or minus square root of a plus y. Now dz is p dx plus q dy. Therefore dz is plus or minus under root a plus x dx plus or minus under root a plus y dy. So now this is separable in dx, dy, dz. So integrating, integral on left hand side is z plus or minus. This is integral of x plus a raised to 1 by 2. So it is 3 by 2 over 3 by 2. Similarly, integral of y plus a raised to 1 by 2 is y plus a raised to 3 by 2 divided by 3 by 2 plus b. So this is required complete integral. If we wish, we can adjust this 3 by 2. So here I can write 3z, and constant of integration can be adjusted as b upon 3 by 2. So if I take 3 by 2 on left hand side, I will have 3z by 2 equal to plus or minus x plus a to the power 3 by 2 plus or minus y plus a to the power 3 by 2. So this is required complete integral, where a and b are arbitrary constants. So now it is not hard to find out complete integral if our equation is in standard form 3. Now some partial differential equations are directly not in standard form 3, but by making some change of variables they can be converted into standard form 3, and then we can use that standard form 3 to find out complete integral easily. So we consider one problem in which we are able to convert our equation into standard form 3. Z square times p square plus q square equal to x square plus y square. So this is not in standard form 3 because you can see z is present. In standard form 3 we must have z absent. So how to convert this into standard form 3? So this I can rewrite as z square p square plus z square q square equals x square plus y square. Now p square is nothing but square of del z by del x. Similarly, z square times del z by del y whole square equals x square plus y square. This I can again rewrite as z del z over del x whole square plus z del z over del y whole square equals x square plus y square. Now this suggests that we should take this change of variable z del z equal to del capital Z. Then from this we obtain small z square by 2 equal to capital Z. This we will use after obtaining complete integral. So if I put z del z equal to del capital Z, and then if I give this number 1, and if I use z del z equal to del capital Z, then our equation will be converted into, then 1 becomes del capital Z by del x whole square plus del capital Z by del y whole square equal to x square plus y square. So putting this z del z equal to del capital Z in equation number 1. So now if I assume that this partial derivative is p and this partial derivative is q, I will have x square plus y square, where capital P is del capital Z by del x, capital Q is del capital Z by del y. So you can see this equation is in third standard form. Now we can separate it out with p square. I write p square minus x square equal to y square minus q square. So it is in standard form 3, so we assume that suppose both are equal to a. So from this I will have p square minus x square equals a, y square minus q square equals a. So therefore p square equal to x square plus a, and similarly q square equal to y square minus a. Now this a is arbitrary constant, so that we can adjust as a square. Instead of writing small a, we will write a square. There is nothing special in writing a square, but to simplify the further steps, we will write arbitrary constant as a square. So therefore I obtain capital P equal to plus or minus under root x square plus a square. Similarly q equal to plus or minus under root y square minus a square. So now once we obtain values of p and q, we put them in this equation. Dz is, this is d capital Z, p dx plus q dy. Therefore d capital Z equals p is plus or minus under root x square plus a square. Similarly q is plus or minus under root y square minus a square dy. So this is easy to integrate now if we know the formulas. So integrating, we get integral of dz is capital Z, integral of this x square plus a square is plus or minus x by 2 under root x square plus a square plus a square by 2 log of x plus under root x square plus a square plus constant of integration is b by 2. Now capital Z is nothing but, before that we have to write integral of this also. So now I first remove this, then I will write down. So plus or minus y by 2 under root y square minus a square minus a square by 2 log of y plus square root of y square minus a square and plus arbitrary constant b. And finally we put value of capital Z, and here we adjust b as b by 2. Now value of capital Z is Z square by 2. So now we put Z square by 2 in terms of Z, because now we have done the process of solution. So therefore capital Z is Z square by 2 equal to plus or minus under root x square plus a square and just a minute, x by 2 square root of x square plus a square by 2. Right hand side there is no change. We are rewriting right hand side as it is log of x plus under root x square plus a square plus or minus y by 2 under root y square minus a square minus a square by 2 log of x. Instead of x we have y plus square root of y square minus a square plus b, where a and b are arbitrary constants. And here instead of b we have written b by 2. So this is required complete integral. In the next step you can cancel out these 2 if you wish, because we have 1 by 2 in each term. So that can be cancelled out, and we will have some simpler form. So in this way, if our equation is in standard form 3, then it is easy to find out the complete integral, and also it is easy to find out complete integral if we have our equation not containing standard form 3, but it can be converted into standard form 3 by some change of variables. So in both the cases it is not hard to find out the complete integral. We can directly or easily find out the complete integral if our equation is in standard form 3. So I hope you like this lecture. Thank you very much.